Okay. It seems, guys, we are posting the video, so you guys are not bothering to attend the classes, huh? See, in the tutorial, when I got so many, say, requests, and even in the feedback form, that we are not covering enough number of problems, then when I have a separate tutorial where I'm discussing the problems, I see just, how many? I think 8, 9, or 10, 3, 4 students are from our section. So I expect that, when you guys are saying that you need more problems, more practice problems, then I expect that you attend the tutorial and get benefited from that. So it seems that now I'm posting the videos, so you do not bother to attend the live classes, huh? Because the video is available, so I can watch the video anytime. Okay, anyways, so let's start. So in the last, 2-3 classes, we were looking at the rectangular waveguides, and then we have seen that, the solution, the general solution to the rectangular waveguide was this one, where F can be a general solution, which can take any 6 components. And then what we did is we applied the boundary conditions, and with the boundary conditions, we were able to get this as the solution for the TE mode. And remember, we focused on TE mode, saying that TM mode, we will just look at it later, and it will be just a summary. We will not go into the derivation because the derivation will be similar. So we looked at the TE mode, and then from there, we first got only one component out of the 5 components. Remember, we have EX, EY, HX, HY, and HZ. EZ will be absent for the TE mode because there will not be any component of electric field in the direction of propagation. So in our case, the direction of propagation is Z direction, so therefore EZ will be absent. So therefore we selected HZ, and the main reason why we selected HZ, because we can use HZ and we can generate the remaining transverse modes, because EX, EY, HX, HY, they are all transverse mode because they are in the transverse plane, okay, which is perpendicular to the direction of propagation. So that's, you can easily get it using Maxwell's equations. That's why we went and then we applied the boundary conditions, and we got this as our HZS field. And then after applying the boundary conditions, we also got this as KX and this as KY. And if you remember, this was the main reason why we are getting the several modes, or I would say the several patterns of our electric field and magnetic field, because whatever satisfy this condition, that is M is equal to, we know several M's and several N satisfied. So each M will correspond to a different field amplitude pattern in the transverse direction. And that's why we are seeing so many modes. Okay. And here, remember, this is still in the phasor notation. So in the instantaneous notation, if you want, in the instantaneous form, if you want, what you need to do, you need to multiply by e power j omega t and take the real part of this. So this can be equal to h naught cos kxs cos ky y cos of omega t minus beta z. This will be the instantaneous, oh, sorry, not beta, since it is gamma. So let me correct it. So you will have e to the power, okay, it will be beta z. Then in that case, we will have the term which is e power minus alpha z. So this is the instantaneous form. Instantaneous form. Okay, so remember again, so whatever we have studied in the previous classes or in the transmission lines or in the EM waves in unbounded media, same thing here. See here, so again it's a traveling wave. Now the only thing is, if you look at this part, your amplitude is not constant. Your amplitude is not constant. Your amplitude is a function of x. Your amplitude is a function of y. That means as you move, so if you see here, if this is your waveguide, and if this is my direction of propagation z, then the field will change its amplitude along these directions. So this is my x direction. This is my y direction. No, let me take it the other way around because it will not satisfy the right hand rule. So this is my x direction, this is my y direction, and this is my z direction. So here the pattern will become is a function of x and y. So it will be a function of cosine. So the amplitude will change according to cosine. And here also for x also it will change according, the amplitude will change. So that will all creating a pattern. So this is in the transverse, in the xy plane. Whereas the same, whatever you are seeing this, they will move in the z direction in a sinusoidal manner that we have seen in the unbounded medium. It's a little bit complicated to visualize, but in the end, I will show you an animation. With that animation, you will be able to understand what's going on. Okay. Then we derived several expressions. If you see here, we derived our cutoff frequency and we said that TE1,0 mode is the dominant mode. And if my operating frequency is less than the cutoff frequency, that means nothing can propagate in the waveguide, and it is called as evanescent wave or evanescent mode. Then if my operating frequency is greater than the cutoff frequency of what? Cutoff frequency of my different modes, then it is called as a propagating. And then what we did, we looked at different derivations. If you see here, we found beta, which is in terms of beta dash. Beta dash is the unbounded medium. And then we found the phase velocity in terms of the phase velocity of unbounded medium, in terms of the cutoff frequency and the operating frequency. Then the lambda, then the cutoff wavelength, and the wavelength of the unbounded medium. And then we took this example where we named all the propagating modes of TE based on my operating frequency. And then for this particular mode, we got beta, U, and lambda C. So for TE2,0, we want to find beta. So what we did, first we found beta dash, which is omega root of mu epsilon, which is omega over U dash. And since it is air field, U dash is nothing but your velocity of light. And that's why we got this beta dash. And once I get beta dash, I can get the beta of my mode, which is beta dash root of 1 minus fc over f squared. And you are using this formula, guys, because we know our operating frequency. That's why. So therefore, I know my operating frequency f, so which is 8, and the cutoff frequency of my TE2,0 mode, which is 6. And I substitute here, and this is my beta. And then similarly, I can find my phase velocity U is omega over beta. Either you can use this because beta you have already calculated, or you can go and you can use this expression also. It's the same. You will get the same answer. Then the cutoff wavelength, which is U dash over FC, and which is 5 centimeters. So this is where we stopped in the previous class. So I gave some good introduction because there was a 2 days gap so that, everything can be brushed up. Now, what we are doing is, till now we are looking at only which component? Till now we were only looking at the HZ component, which is this component. See, which is only this component. We solved the wave equation only for this component. We applied the boundary conditions and other things. Now here what we are doing is we are trying to find the other components. So we only have HZS. And now from HZS, How can I find the remaining TE components? The remaining TE components will be EXS, EYS, HXS, and HYS. Remember, this is a TE mode. See, it is TE. So in TE, EZ will be 0. Why? Because there will be no component of electric field in the direction of propagation. And what is the direction of propagation here? See, is the plus Z direction. So therefore, my EZ will become 0. So how do you find this? Again, as I told you, this was the main reason why we went and solved HZS, because I can straight away use Maxwell's equations, and then from the Maxwell's equation, you can easily find the different field components. And all this derivation of the different field components, guys, it's there in your textbook. So we will not go into the detailed derivation, but it's available. So you can look at it in your textbook where it is. So if you see, yeah, if you look at your, I will give you the page numbers if you want. You can look at the page number 616 and 617 of your textbook. Okay, so there you will see how they have used the Maxwell's equation, which is del cross ES bar is equal to minus J omega mu HS. And the second boundary condition, del cross HS bar is equal to J omega epsilon ES bar. So we can apply these two Maxwell's equation, and in that, if we substitute our HSS, then we should be able to find the remaining components. That is the very good advantage of solving HZS component. Okay, so this you can look at home, look at later from the textbook. So these are the field components. So the remaining 4 field components, which is the transverse field components, you can see. So you have EXS, EYS, HXS, HYS. These are all called as the transverse field components. And why they are called transverse field component? Because they are perpendicular to the direction of propagation. They are in the transverse plane. And in our case, XY is the transverse plane because Z is our direction of propagation. And these are see how they look like. So if you see here, if you compare them, so they are all, if you compare them, so they are all propagating in the Z direction. See, they are all propagating in the Z direction. And they are transverse in the transverse plane. Here, see, this is a function of X and Y. Can you see this? So this is and it is cosine. But here, it's a function of cosine sine. See, function of X, function of Y, cosine sine. This is sine cosine, function of X, function of Y. This is again sine cosine, and this is cosine. And if you can see here, there is a new term that has been say named here, which is called as H square. And H square is nothing but M pi over A square plus N pi over B square. Okay, so these are the field components whose again amplitude of their waves, they will change in the X and X in the transverse directions X and Y according to again cosines and sines, all of them. And now the last and very important point is, till now we have been saying that you cannot have m is equal to 0 and n is equal to 0 together, right? You cannot have m is equal to 0 and n is equal to 0. We cannot have this. We cannot have this one together. So here you will see, till now I have been saying that in the end, nothing will exist. Everything will vanish. Here you will see. Now, if you put n is equal to 0 or m is equal to 0 here, then you will see that when they both become 0, all the transverse field component disappears. They all disappear. They all become 0. And your HZS will just become H0. So they, all the cosine terms and everything will vanish. This is just a constant. And we know that this is not an EM wave. So that's why M and N cannot be 0 simultaneously. And that is the reason TE 0,0 mode doesn't exist. This does not exist. And that's why our first mode is TE 1,0. That is our first mode. Okay. Now, as I have already told, they are all propagating mode in the plus Z direction. They have same betas. See, they all, if I know the amplitude of my HZ, then I can find the amplitudes of all these components. Because if you see, all these components have H0, which is the amplitude of my HZ mode. Okay. Now, the next part is what is called as the intrinsic impedance. So very similar to what we have seen in our unbounded medium or in transmission line. So here we also have the intrinsic impedance of a TE mode. So in the intrinsic impedance of a TE mode, for this particular case where we have the direction of propagation in the Z direction, then in that case, eta TE is equal to EX over HYS, EXS over HYS. Very similar to your unbounded medium. But here, because it is bounded medium, so if you divide this field by this field, whatever we have got just now, then you will end up with this part, which is equal to omega mu over beta, which is equal to U times mu. And you can replace U with U dash divided by root of 1 minus FC over F square, and then simplify it. And then you will get this as your answer. So your intrinsic impedance is, this is called as the intrinsic impedance of the unbounded medium. Unbounded medium. So our main objective in this derivation is we are trying to get our intrinsic impedance in terms of the intrinsic impedance of the unbounded medium and the operating frequency and the cutoff frequency. So this is the intrinsic impedance of the TE mode. Now, in a similar way, where it is, yeah, in a similar way, you can also get the intrinsic impedance. This is very similar to our unbounded case. You can also get it like this, EYS over HXS. That is also the intrinsic impedance, but it will be a negative. This is what we have also seen in the unbounded medium. Why? Because we know E cross H must point in the direction of propagation. So the negative sign is included in the intrinsic impedance. So this is the intrinsic impedance of our rectangular wave. Okay, so now let's take an example. So what is this example? The example is saying that you have an air-filled rectangular waveguide which is operating at 5 gigahertz. That means my operating frequency F is 5 gigahertz. And this is my dimension A, 4 centimeters, B, 2 centimeters. Now we know that for the dominant TE 1,0 mode, the Z component of the magnetic field is given by, okay. So the magnetic field component is now given to us, which is HZS is 0.1, which is, see, this is H0. If I compare it with my standard expression, cos KXX, cos KY by e power minus J beta Z. Now we need to find Kx. Guys, one more thing. Remember, in the starting, I put e power minus gamma, e power minus alpha Z here. But remember, in the derivation, we have seen that alpha will become 0 for the propagating mode. Okay, we have seen this. So for gamma, which is alpha plus j beta, for my propagating mode, alpha becomes 0 and gamma becomes minus j beta. Sorry, gamma becomes j beta. This is for the propagating mode. So alpha becomes 0. Okay, so what we need to find? We need to find Kx, Ky, the phase constant beta, and then we need to write the expression of HZS, and then we need to find the intrinsic impedance, and then we need to find the expressions of all the transverse field components of my TE1, 0. So how should I go? So first we will find Kx and Ky. So we know that Kx is m pi over a, m is equal to 1, a is 4 centimeters, so 0.04, so it is 25 pi. Ky is n pi over b, because this is our fundamental mode or the dominant mode, which has the least cutoff frequency. So its n is equal to 0, so Ky becomes 0. And what will be the cutoff frequency of this particular mode? The cutoff frequency is u dash over 2a. Why it is u dash over 2a? Because it's a fundamental node or it's a dominant node. It's a dominant node. So therefore, we can directly use this expression, because this is the expression, if you remember, guys, we derived for the dominant node. We derived it for the dominant mode. So we use this, and this is the our cutoff frequency, 3.7 gigahertz. And if you see now, our operating frequency is what? 5 gigahertz. And what is the cutoff frequency of my dominant mode? 3.75 gigahertz. So from here, what can we conclude? Yes, maybe Nawaf, can you tell me? What should we conclude about my mode? So if my operating frequency is 8 gigahertz, and if my cutoff frequency of my TE1, 0 mode is 3.75 gigahertz. So will my TE1, 0 mode is propagating or it is evanescent?
I think it's propagating.
It is propagating. Why it is propagating? Again, go and look at the condition. So your F should be greater than FC. If F is greater than FC, that means it's a propagating mode. This is what we checked now. And after checking this, we made sure that yes, my dominant mode is propagating. And now I'm proceeding and I'm finding the remaining terms. So what more we need to find? We need to find beta dash. So beta dash is the phase constant of the unbounded medium, which is omega over u dash. So it is 102.47 radians per meter. And then I will find the beta of my TE1, 0, which is nothing but beta dash root of 1 minus FC over F squared. So FC, I found it. F operating frequency is 5, and this is my beta. And therefore, now I will substitute Kx, Ky, and beta here to get the expression of HZ. So Ky is 0, right? Because cos 0 is 1. So therefore, only this term will be left. So that's why you have 0.1 cos 25 pi x e power j 67.79 amperes per meter. This is the phasor notation of my magnetic field component HZS of my TE1, 0. Then it is asking you to find the intrinsic impedance of the TE. So therefore, intrinsic impedance, we do not require any expressions. We have just now derived expressions of the field components. We already got it. It is nothing but eta dash over root of 1 minus FC over F square. And eta dash is unbounded medium. And if you see here, my unbounded medium is air. So that's why it is 377 over 0.677. So it is 556.22 ohms. Now, last part, write an expression for all the transverse field components of TE1, 0. So remaining, that which is EXS, EYS, HXS, and HYS. This is what is asking. So, but when we know M is equal to 1 and N is equal to 0. So therefore, I'm first finding H square, which is M pi over A square plus N pi over B square. So this is my H square. So H is nothing but 25 pi. And then I'm now substituting this in all this field components that we have derived. 1, 2, 3, 4, all this field components, 4 field components. So we know that Ky is 0, right? Our Ky is 0, or I would say N is 0. So if N is 0, then what are the field components that we can get? See here. So if you see here, this is EXS. So N is 0. N is 0. So therefore, sine 0 is 0. That means EXS becomes 0. When EXS becomes 0, then I can say its corresponding magnetic field or its associated magnetic field component, HYS, will also become 0. Why? Because we know EXS over HYS must be equal to eta, right? So if this is becoming 0, that means HYS is also 0. So these and this EXS and HYS doesn't exist. Now we need to now go and find EYS. So this is the EYS expression. And in this EYS expression, if we substitute M, N, H, then K, we substitute all of them and then simplify. This is YE. So EYS exists. Now, once EYX exists, then its associated component, associated magnetic field component. Why? Because EYS over HXS will give me minus eta TE. So if this exists, then I can find its associated HXS as HXS is equal to this over eta, and this is my HXS. So therefore, in summary, if you see, these are my field. So I have only HZS, my EXS and HYS is 0, and I only have EYS component and HXS. So in summary, for your TE1, 0 mode, for TE1, 0 mode, your E electric field is nothing, has only Y component, see, which is equal to AY minus AY J 0.503 sine 25 pi x e power minus j 67.77 volts per meter. I would say S because this is in phasors. This is my electric, and therefore, and my magnetic field will be X component AX plus Z component, 2 components. And what is HXS? This is HXS. And what is my HZS? This is my HZS. So this is equal to AX bar J 9.03 times 10 power minus 4 sine 25 pi x plus AZ 0.1 cos 25 pi x. I can take common and I can say it is e power minus j 67.77 amperes per meter. This is my magnetic field HZS. Sorry, not Z. HS. Got it? So these are the field components of my TE1, 0. So in a similar way, you can get it for other modes as well. Okay. Now, with this, guys, we conclude our TE mode say analysis. So we have analyzed our TE mode from whatever aspects that is required for our course. So now, as I told you, for the TM mode, we will not go and do all this derivation because we have comprehensively looked at the boundary conditions. We looked at the solution of the wave equation, and then we solved it for a general, function Fs, and then we replaced Fs with HZS, and then applied the boundary conditions and got the HZS expression. So we did all these for the TE case. So for the TM case, we will not derive, but we will just do a comparison and see where the changes are. So if you see here, this is what we are doing in my lecture number 39, that we will not derive for the TM modes of the rectangular waveguide because it is similar to the TE modes. But here we will we have just summarized them. So this is the summary of the TM modes, and we will compare it with TE modes. So if you see here, so let's do the comparison. So we will follow the similar steps. So what are we going to do? We are going to start with solving the field component, which is in the direction of propagation. See, it is TM mode, right? And if my direction of propagation is plus Z direction, that means according to the definition of TM mode, there will not be any field component. Which field component? The magnetic field component in the direction of propagation. So that means HZS will be 0 here. And then I will get EXS, I will get EYS, and I will get HXS, and I will get HYS. In addition, I will also get EZS. And here also we will do the same thing. We will first try to solve for the field component which is in the direction of propagation, very similar to our TE case. Because in our TE case, we have EXS, EYS, HXS, HYS, and you will also have HZS. Okay, so if we do it in a similar manner, we will get this as my component. And see here, you have both sine and sine, but here you have cosine and cosine. Here, M can take from 0 and N can take from 0, but we know it very well that both cannot be 0. But here, no. M and N, if you see here, they are starting from 1. So M can be greater than or equal to 1, and N can be greater than or equal to 1 independent. Okay, that means you can have both taking 1 and 1 simultaneously. It is possible. For example, TM 1, 1 is possible. It can exist. But here we have seen that TE00 cannot exist. So therefore, this dominant mode is TE1, 0. And here are the remaining components, the 4 components. Here are the remaining 4 components. Again, they are sine and cosines, you can see here, and they are all a function of H. H we have already defined, which is kx squared plus ky squared. See, which is m pi over a square plus n pi over b square, is nothing but kx square plus ky square. And kx is m pi over a and ky is n pi over b. This is same for both of them. And now the intrinsic impedance here, the root is in the denominator, but here when we derive, you will see that the root becomes will be in the numerator. So this is a very important key difference. Okay, so it's a key difference. Yes, this is also the key difference, but this is also another key difference of the TE and TM. And then if we move further, the remaining things, they are all common. If you see here, they are all common. So first thing here, TE1,0 is the dominant mode, but for TM, there is no dominant mode for TM. Okay, for TM, there is no dominant mode. The dominant mode doesn't exist because only the dominant mode exists in one TE case, and it's a unique one. There cannot be two dominant modes. There is only one. So it exists in TE, so therefore it doesn't exist in TM. And the remaining things, they are same. The cutoff frequency expression is the same. And just now we have seen F is less than FC, it's evanescent, greater than FC, it's propagating. And for the propagating modes, alpha is equal to 0 and gamma is equal to J beta. And the phase constant expression is the same, U, lambda C, and the eta, which is HYS is equal to EXS over eta, or HXS is equal to minus EYS over eta. So these are all same. So if you see, there is a lot of similarity between your TE and TM modes, and their derivation is also very similar. So that's why we comprehensively looked at this TE in our last 3 classes, and now we are seeing that TM is similar. Okay, and by the way, this table is there in your formula sheet of your exams. Okay, now let's take an example. So the example is saying that you have an air-filled rectangular waveguide. So it's air-filled, and this is the dimensions. So the dimensions are A is equal to 5 centimeters and B is equal to 2 centimeters. Now, arrange all the modes according to their increasing cutoff frequencies up to 10 gigahertz. So it is saying that you need to just find all the cutoff frequency and you have to arrange it in the ascending order up to 10 gigahertz. So how should we proceed? In a very similar manner as we did in, I think, the last class. So first, we make m is equal to 0. M is equal to 1 and n is equal to 0. And we know the expression. Fc is equal to u dash over 2 root of m over a square plus n over b square. Substitute 3 gigahertz. Then make n fixed and increase m to 2. Then 6 gigahertz. It is under our it is below 10 gigahertz. Then m is equal to 3 and n is equal to 0. 9 gigahertz is okay. Then m is equal to 4 and n is equal to 0. Now it is becoming 12 gigahertz. So it is out of range. So stop here. Stop here. Then now what we will do, we will go back and we will repeat for m, but by making n is equal to 1. So n is equal to 1. Let's see here, n is equal to 1 and m is equal to 0. So it is 7.5 gigahertz. Then moving further, let me make it smaller. Then, so this is m is equal to 0, n is equal to 1. Then m is equal to 0 and n is equal to 2. If you see here, this is 15 gigahertz. Again, it is out of range. So stop. So that means n is equal to 1. is the maximum. So this is for the TE, right? Now let's start for TM. So if you see for TM, as we know, it starts with m is equal to 1. So m and n, the smallest values they can take is 1, 1. So we start with 1, and we will do it. So it is 8.077 gigahertz. And it will be same as TE1, 1, right? Guys, because the formula for the cutoff frequency for TE1, 1 and TM1, 1 will be same. See, it is FC is U dash over 2 root of what is this m over a square plus n over b square. And this is same for both TE modes as well as TM modes. So therefore, the cutoff frequency of this and this will be the same, which is 8.07 gigahertz. Then I'm making m as 2 and n as 1, 2, 1. Then again, I'm getting this. Then I'm making m as 3 and n as 1. But this is out of. After that, you can go ahead and you can try this. You can try TE and TM. You can try by making n is equal to 2 and m is equal to 1. But you will see that this will also be more than 10 gigahertz. It will be more than 10 gigahertz. So that means finished. And now we have to just write it in the ascending order. So in the ascending order, according to the frequencies, these are the order. First TE1, 0, then 2, 0, then 0, 1, then both of them, then this one, and then this one. So what is the takeaway message from this example? So the takeaway message is that as your operating frequency increases, then these modes will become guiding in this order. See, in this order, they will become guiding. So first, the dominant mode becomes guiding. Now, after dominant mode, which mode will become guiding? TE2, 0 mode will become guiding. Then this will become guiding. Then both of these will become guiding. That means now TM mode will also come into picture. Then this mode will be guiding, and then this mode will be guiding. And now all these modes, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. All these 8 modes has different transverse patterns. And they are all traveling with the same phase constant in the direction of propagation. So the energy of your signal will be carried by all these modes together. Okay, they will be carried by all these modes together. So this is the example. So the main objective of this example. Okay, now you have this last question, and the last question is saying that this is an example of a TM mode. So it's saying that our operating frequency F is 12 gigahertz. It is air filled, and its operating frequency is 12 gigahertz. The waveguide dimensions are 4 centimeters and 2 centimeters, and the Z component of the electric field of the TM11 mode. So we are talking about TM mode. So that means M is equal to 1 and N is equal to 1 is this one. So this is the electric field component of the TM mode, which is EZS. It is given as 20 sine KXX sine KY by e power minus j beta z. And first we need to verify whether this mode TM1, 1, it is propagating or not. And then we need to find KX, KY, beta, and then write down the resulting expression of EZ. Then you need to find the phase velocity, the intrinsic impedance, and the other components. Very similar to what we did in the dominant TE1, 0. Okay, so I will quickly go through because we have done this similar problem in just say in the starting of the lecture. So first, how do you check whether the TM1,1 mode is propagating or not? Yes, how do we check? Muhammad Al-Bosh, you are there? Muhammad Al-Bosh? No? Hassan? Okay, I think he's here. Yes, Muhammad Al-Bosh, can you tell me how do we check? How do we check whether TM11 mode is propagating or not? Yes, Mr. Muhammad Al-Bosh, what happened? No answer? Maybe Hassan? Hassan Bashamakh, you are here or no?
Yes, doctor.
Yeah, maybe can you help?
Well,
Help Mr. Muhammad Al-Bosh. Can you check? Can you tell me how can we check this? What should we do?
I don't know really.
Hassan, come on, you cannot tell this. We just did an example. Anyone else
We
can
calculate
help?
the cutoff frequency.
Sorry?
We calculate the cutoff frequency.
Yes. So first
Compare.
calculate the cutoff frequency, and after that, what should I do?
Compare with the operating frequency.
Yes, compare with the operating frequency, and then
If the operating frequency is larger, then it's propagating.
then it is propagating. Thank you very much. So this is what we did just now. So therefore, let us do the same thing here. So you first find the cutoff frequency. See, cutoff frequency of my TM1,1 mode and compare it with the operating frequency. My operating frequency is 12 gigahertz. So 12 gigahertz is greater than 8.3 gigahertz. Therefore, my TM1,1 mode is propagating. Now you can find Kx, Ky, beta. See, Kx, Ky, beta in a very similar way that we did in the starting of the class. And then you can get the easy component. And after that, you need to find u. You know the expression, u is u dash over root of 1 minus fc over f square. You can get the u, or you can also get as omega over beta. Then the intrinsic impedance is eta dash root of 1 minus fc over f square. And eta dash is for the unbounded medium. It is A, so it is 377, and you get this. And last, the components, again, you go first find h, and you have the expressions. And if you substitute in the expressions, you will get all the components. So this is hy, this is ex, and this is hx, and this is ey. Okay, so this actually, guys, concludes our rectangular waveguide chapter. So in the next class, which is on Tuesday, we will take a quick review of this one, and then we will move to the next application. Okay, so thank you very much. If you have any questions, you can ask, and the class is officially finished. You can leave, and if you have any questions, you can ask even in the next class.